Now, take a look at the lattice translation vector. We introduce lattice translation vectors. In a crystal, if you move from one lattice point to another by an allowed translation, the atomic environment remains identical. So mathematically, if we write R prime, so look at the slide. The slide we have the R prime. R prime, R yang ada tanda atas tu, this is R prime. I don't know whether you could see my cursor or not. This is R prime. We have two R primes, one in the equations and one more in the diagram. Mathematically, if we write R prime equals to R plus N1A plus N2B plus N3C, where the N1, N2, N3 are integers, any integer, this means the crystal repeats periodically in space. The vectors A, B, and C define the periodicity of the lattice, whether in different axes. Could be could be X, Y, and Z axis. So this idea of periodic repetition is extremely important, because later in the reciprocal lattice, we will also build from periodicity, but in different space. Now we are still talking about the real space where the atom is located, exactly the space. Later, the same concept also, we will reconstruct from the diffracted wave of X-ray into reciprocal lattice. From that construction, we could predict what kind of crystals are there actually in the real space, right? So let us take a look at the next slide. There you go. We have primitive versus non-primitive unit cells. We need to be able to distinguish between primitive and non-primitive unit cells. A primitive unit cell is the smallest repeating unit that can reproduce the entire lattice through translation and contains exactly one lattice point, the smallest crystal that is going to be repeated. So be careful here. One lattice point does not necessarily mean one atom, because the basis may contain more than one atom. Could be molecule, and the molecule could contain more than one atom, 2, 3, 4, 5, or even 8. Depends on the material. So for conventional cells, we often count the contribution from corners, the corner of the, imagine like a cube. Okay, we should often count the contribution from the corners of the cube, the faces of each cube, or the center of the cube itself, which will be related to the body-centered cubic later. So in a simple cubic, we have 8 corners of atom. 8 corners atom. Sorry, 8 corners atom. Each atom at the corner of the cube. Imagine if we have simple cubic crystal, we have 8 atoms at each corners. So in one corner, we have 1/8 of an atom. At the corner of the cube, simple cubic, there will not be one atom, but we have 1/8 of the atom. Bukan suku, tapi 1/8 daripada atom tersebut. It's about 12.5% of an atom. So in total, we have 8 corners in one simple cubic. So in total, 1/8 times 8 corners, we have 1 atom in a simple cubic crystal. So in body-centered cubic, we have atoms at the corners. Also, at each corner, we have 1/8 of an atom, or could be molecules. Okay. So we have 8 corners. Therefore, in total, we have 8 atoms. Plus, we have 1 specific atom inside the cube itself. So from the center, we have 1 atom at the center. Sorry, from the corners, we have In total, 1/8 times 8, we have 1 atom. And inside the cube itself, we have 1 atom, and plus them together, we get 2 atoms in a body-centered cubic. Now, how about in face-centered cubic? Look at the slide. We have 4. Why 4? Okay, from the corner, we have 1/8 times 8. We have 1 from the corner, and from the faces of the cube, there will be 1 atom at each face of the cube. So in one cube, we have 1, 2, 3, 4, 5, 6. We have 6 faces, and each face, the atom is divided into 2. So each face contains 1/2 of an atom. So half of an atom, we multiply by 6, we got 3 atoms. So 3 atoms from the faces and 1 atom from the corners. We have 4. In total, becomes 4 per conventional cell. So if we are talking about simple cubic, we are referring to 1 at 1. BCC, body-centered cubic, we are talking about 2. Face-centered cubic or FCC, we are talking about 4. 4 per conventional cell. So conventional cells are useful for symmetry, but not always primitive. Try to separate in your mind smallest repeating cell versus most symmetric cell used for description. Oops. Hold up. Something's not right. All right. There you go. Now look at the next slide. Let us try to see the weakness sites primitive cell. Weakness sites primitive cells. Huh? What does it mean by weakness sites primitive cell? A second way to define a primitive cell is through the weakness sites construction. We need to be able to construct a weakness sites primitive cell. The procedure is we need to choose one lattice point as reference. That is number 1. Yep, mana dia? Okay, as mentioned in the slide, choose any lattice point to be the origin that will become the center of your construction. Okay, any lattice point, up to you, doesn't matter. Next, draw lines connecting to its nearest neighbor. That's what we have been doing. Okay, we choose the red one first and draw lines connecting this point to all its nearest neighboring lattice point. So the nearest neighboring lattice point are these points, the blue ones, the nearest one, only the nearest one. Okay. And we draw the lines connecting this point. So the first line over here, second line, the dotted line, see the dotted line or the dashed lines. Okay, the line, we have the lines, okay, connecting the first reference point to the neighboring and points. Now, what's next? Bisect the line. Bisect the line. Make sure you draw a line exactly dividing the dashed line that you have drawn just now. So for example, if this one, I think I need to draw using this one. Yeah. Okay, let's say we are drawing this line. Let's say we are drawing this line. So we need to bisect it. Maksudnya bagi 2 garisan tu. Itu dia, bagi 2. Garisan ini pula yang mana? Bagi 2. Ini dia bagi 2. Garisan yang ni pula macam mana? Kita bagi 2-nya. How about this line? Divide it into 2, this one. How about this line? Divide it into 2. How about this line? We divide it into 2. Done. Okay. So we have like a Star of David kan. Nampak? Saya bukan pro negara yang tak sepatutnya disebut nama tu. No, tak. Kebetulan contoh ni jadi macam ni. Kebetulan. Nampak macam the Star of So what's next? Mana tadi? Ni. identify enclosed area. Now, from your drawing, identify the smallest region enclosed by these bisectors. See the crossing of the bisectors, nampak the bisectors? But bisectors, the crossing bisectors, we are actually choosing this one, the crossing line. Nampak ni, kita ada apa? 1, 1, 2, 3, 4, 5, 6. So we have hexagon. So this hexagon shaped area enclosed by the bisectors, this is the weakness sites primitive cell. This is only the basic first, the basic first. This is the weakness sites primitive cell. This is primitive cell, the smallest structure, right? And this is the weakness sites primitive cells. Okay, what's next? So this construction is purely geometric. It defines the region of space closer to the chosen lattice point than to any other lattice point. This idea becomes very important later because in reciprocal space, the same construction gives us the first Brillouin zone. What is Brillouin zone? Nanti kita tengok what does it mean by the Brillouin zone. So if you understand the weakness sites in real space, you are already preparing for the Brillouin zone in the reciprocal space later. Remember, this is weakness sites. We are still talking about the real space. Yeah. Brillouin zone nanti dekat the reciprocal space where we will construct based on the diffracted X-ray. Okay, now I think we stop for a while. Later we continue with the X-ray.